Mod-Arg Form is what we're going to look at here. So modulus is basically the length of the vector. Well, let's plot a point in. There's a complex number, x plus iy, and we saw yesterday that we could plot every complex number in a unique position. But if we create a position vector by joining it up to the origin, then we can talk about our complex number in another way. One, the length of the vector, so that's what we call the modulus, and we can work that out, and look what we get. X squared plus y squared, symbolised with, well, the absolute value symbol, which means length, which means modulus. And the other piece of information is what we call the argument. And the argument is the direction of the vector, so the angle that it makes. Inverse tan of y on x is how we find it, but this is the important bit. We only talk about acute or obtuse angles with the argument. And then the plus or minus just tells us whether we're above the axis or below the axis. So all our answers for argument will be in between minus pi and pi. Notice it doesn't include minus pi, because pi and minus pi would be in the same position if you think about it. So it's pi we'd call it. 4 minus 4i, let's find the modulus. So square root of 4 squared plus negative 4 squared, we get 4 root 2. And the argument, inverse tan. Now note I've written it as minus 4 on 4. I haven't written it as minus 1. It is of course the same as minus 1, but there is a reason why I wrote it as minus 4 and 4. Because it's important that I see which quadrant it's in. So then I know whether I want an obtuse angle, whether I want an acute angle, positive or negative. Now you might not draw the diagram, you might think about it, but in this one the imaginary part's negative, the real part's positive, so I'm over there in the fourth quadrant, so we're talking about an acute angle, it's below, so it must be a negative acute angle, minus pi on 4. Now every complex number then can be written in terms of the modulus and the argument, so it's another way of describing a complex number. So instead of using the real part and the imaginary part, we use its modulus and its argument. So we know that z equals x plus iy, there it is in its component form if you like. But we now know we could also write it this way, because using a bit of trig on that triangle we had, the x value would be r cos theta, and the y value would have been r sine theta. So there we have it in terms of its modulus and its argument. Now r will always be a common factor there, so we can pull that out. We get cos theta plus I sine theta. So the Mod-Arg form, cos theta plus I sine theta. There is a shorthand way of writing cos theta plus I sine theta, and that's cis, because the angle is always going to be the same. So this saves us writing all the time, and so cis stands for cos plus I sine. Be careful when you're using that notation though, because it's very easy to write cos instead of cis or vice versa. And so r represents the modulus, theta represents the argument. So back to our 4 minus 4i, there it is in its component form, but we now know we could rewrite that as 4 root 2, the cis of minus pi on 4. What about root 3 plus I then? Okay, modulus turns out to be 2. Argument, 1 over root 3. They're both positive, so I know I'm in the first quadrant. Therefore, I'm looking for an acute angle. Inverse tan of 1 on root 3 is pi on 6, isn't it? So 2 cis pi on 6. Now, if we want to go back to the other way round, that's where we need to remember what cis actually means, because we'll write it that way, and then we can work it out. What is the cosine of pi on 6? What is the sine of pi on 6? And expanding out, there it is, 3 root 3 plus 3i. So some relationships, how do we play with them when we're in this Mod-Arg form? Okay, if you want to find the modulus of 2 complex numbers multiplied together, it's another one of those ones where it doesn't matter which way round you go. You could multiply the 2 numbers together, then find the modulus, or find the modulus of each individual one and just multiply those numbers together. Argument though is different. It's a bit like logarithms. When you multiply together, you actually add the arguments. Add the arguments. Note, this goes back to something I mentioned yesterday. Multiplication rotates Z1 by the argument of Z2. Now yesterday I just said multiplication by I was a rotation of 90 degrees. Well, this is why, because the argument of I, if you think about where you would plot I, so 1i up on the y-axis, its argument is pi on 2, 90 degrees. So if you're adding 90 degrees to it, you've rotated it 90 degrees. So multiplication is rotation. I'm going to prove it. Okay, so I'm going to have two complex numbers. One I'll call R1 cis theta 1, the other one R2 cis theta 2. So that's what I'm multiplying together. Well, the modulus is very easy to prove, because all I've got to do now is go, well, R1 times R2. But let's expand out those parentheses. I'll get cos theta 1 cos theta 2 plus I sine theta 1 cos theta 2 plus I cos theta 1 sine theta 2 minus sine theta 1 sine theta 2. And I don't know if you can see it or not, but a familiar friend is there. Let me just rewrite it another way. Cos cos, sine sine. If it's not the sine, it's not the sine. And look at the second one. Sine cos, cos sine. If it's the sine, it's the sine. Therefore, I could rewrite that as cos theta 1 plus theta 2 plus I sine theta 1 plus theta 2, thus proving we add the arguments together. So there we have it. There's the proof for the modulus. There's the proof for the argument. It logically follows then, if you have several multiplied together, to find the modulus of the new number, you could find the modulus of each individual one and just multiply that all together. If you want to find the argument of the new number, you'd be adding the arguments of all the individual complex numbers together. Division, a similar thing happens. I'm not going to prove this one. But so for the modulus, we can divide first, then find the modulus, or the other way around. The argument will end up subtracting. So again, very much like logarithms. Now if I had a mixture of a whole heap there, I've got z1 times z2 over z3 times z4. Yes, I could find the individual moduli and work it out there. With the arguments, basically, if it's on the top of the fraction, I'm going to go plus that argument. If it's on the bottom of the fraction, I'm going to go minus that argument. So it'll be arg z1 plus arg z2 minus arg z3 minus arg z4. Z to the power of n then. Well, the modulus of z to the power of n, I could think of it as mod z times 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 z, like n of them. Well, we said we could find each individual one first if we wanted to. So I could have said that's the same as mod z times mod z times mod z times mod z times mod z times, and so on. So we get mod z to the power of n, basically. But what will happen with the arguments, we're going to add each time. So it would be the argument of z plus the argument of z plus the argument of z plus the argument of z, and so on and so on. I'll end up with n lots of arg z. Notice again, very similar to our log laws. Power, bring it out the front. So let's find the modulus and argument of this particular expression. Yes, I could do the calculation first, but I'm not going to, because it's much quicker to do it this way. Find the modulus of 5 plus I, then the modulus of minus 2 minus I, divided by the modulus of 3 plus 2i, and we end up with, oh, isn't that nice? 13 goes into 26. That was lucky. Root 10 as our final answer there for the modulus. The arguments, okay, here's where I've got to be careful. So is it going to be an obtuse angle? Is it going to be an acute angle? And so 1 over 5, well, that one's in the first quadrant, so that'll be acute. The next one, -1 on -2. So where are we? We're over in the third quadrant. So we've got a negative obtuse angle there. And minus, because it's on the bottom of the fraction, 2/3, again, that's an acute angle. I've gone the degrees here rather than radians, but there's our answer. Shifting the reference point. We see this a lot in coordinate geometry. Classic one is the circle there. If I move the centre of the circle from the origin to 1, 2, it becomes x minus 1 squared plus y minus 2 squared is equal to 1. Well, the argand diagram is very similar to the number plane, so same sort of ideas apply. So there is our complex number x plus iy, which could be represented by that particular vector there. So the modulus of z means the distance from z to the origin. And the argument of z, that's the direction of that particular vector. But what about if I join z to a different point? I'm going to join it over there to W. Think about what we just seen in vectors. Head minus tail. So the modulus of that vector, whatever that vector is, would be the modulus of Z minus W. The argument would be the angle that that new vector makes with the horizontal. So I've just labelled it alpha. So those ideas we just looked at in vectors will come into play now in complex numbers as well. 1D.